Sorry about that. Oh. Can you hear me now? Yeah. I'm so sorry. Okay. All right. So here's the difference. In a least square design, first of all, you see that the ripple kind of drops away, because that actually, having a lot of ripple puts a lot of error on in the least square sense. Okay, but having something below a certain level in the min-max case doesn't incur any penalty, right? So they're very different. One advantage, for example, for the min-max case is that it's a little bit sharper. You see that the transition, it goes a little bit forward and then it ends earlier. So it trades off the amount of ripple in the stop band and pass band for a sharper filter. Okay, sharper transition. But it doesn't attenuate the frequencies over here as much as the least square one, right? So you get something different based on your optimality criteria. Okay? What really least square design, it minimizes the energy in these regions, for example. Okay. That's what it really does. Okay, so the question is, how to design this? Okay, how would you actually implement this? And the idea is to optimize through optimization. Okay, so what we're going to do is we're going to sample or effectively discretize the frequency response. So if this is the frequency response that we're going to be designing, what we're going to actually be looking at, we're going to look at discrete frequencies. Okay? We're only going to look at the frequency response at discrete places. So we're going to fix the sample points to WK equals K times pi over P, where P is how many places we're going to be evaluating our penalty. Okay, we're going to evaluating this mean square, the square error. Instead of evaluating it on the continuum on all omegas, we're going to evaluate it at a discrete number of points. And there's going to be P number of points we're going to evaluating it. Okay, our filter is going to be size m plus 1. Okay, that's the size of our filter. If we just computed a DFT, that will be just m plus 1 points. But we're not going to just evaluate on m plus 1 points. We're going to evaluate the frequency response on way more points than that. The rule of thumb is that we're going to evaluate at about 15 times more points than the order of the filter. Because in that case, there's really little chance for the actual frequency response to oscillate a lot between where we're evaluating them on. Okay? Remember when we compute the DFT, right? For example, the DFT of a constant signal, right? Then you just get a delta function in the DFT, right? It's just an impulse. But we know that the actual frequency response oscillates quite a bit, right? It's really like a periodic sync. The actual frequency response of a constant finite signal, okay, like a rect. We know that it oscillates more. So what we're going to do is we're going to evaluate the frequency response at way more fine sampling than the order of the filter, in the hope that it doesn't oscillate between the points that we're evaluating so much. Okay, so it will give us a really good approximation of the original problem, which is minimizing the square error of the continuous case. Okay, so we're oversampling the frequency response when we're going to evaluate these penalties. Okay, you're going to see actually how it actually works. So we're going to design an m plus 1, which is a 2n plus 1 filter. Okay, so m plus 1 equals to 2n plus 1. So m equals 2n. We're going to first design a non-causal, okay, and hence a non-causal frequency response. Frequency response that doesn't have this linear phase in it, okay, because we're gonna make it causal afterwards, but we're just not going to think about this linear phase that we need to apply. Okay, so we're going to design a non-causal zero phase kind of a filter, okay, which we're going to put a tilde on. And then after we design it, we're just going to shift it to make it causal, okay, or apply a linear phase in the frequency domain, which is exactly the same. So after we design it, we're going to basically shift it to make it causal, and we're going to shift it by m over 2, okay, to make it causal. So now the question is, like, how do you design it? How do we do this? Okay. We're going to formulate it as a matrix problem. Okay. The variables, which we don't know what they are, okay, h tilde, are the unknowns. We want to find how many unknowns we have? 2n plus 1, or m plus 1. Okay, so on both sides, so it starts from h tilde of minus n, right? Because we're designing a non-causal filter first. Okay, all the way to h tilde of n. Okay, these are just unknowns. Okay, those we want to find. Okay, and we have m plus 1 number of unknown variables. Now, what do we know? Well, we know that our desired frequency response, that will be our vector b. Okay? There we're going to just put the right values of the desired frequency response. So we have p number of points in the frequency domain that we care about, okay? Because we're going to sample the entire frequency domain from minus pi to pi very finely with p number of points that are at least 15 times number of m, right? At least, so it's very, very fine. And we're just going to say, well, b, the b vector is h sub d, which is the desired one, at omega 1, and then omega 2, and then omega 3, and then omega 4, all the way to omega p. This is a desired vector. Okay? So what we really want to find is, well, if I computed the frequency, the DTFT, or evaluated the frequency response of H, which is our filter, at certain frequency positions, that should be close to the desired one. Now I need to find an operator, or to compute the frequency response at those frequencies. How do I do that? I create a matrix that actually calculates the frequency response. Okay? So you remember in one of the early labs, you had to compute the DTFT using a matrix operation. Remember? I think lab 1 or something. You had to approximate the DTFT and evaluate it at discrete number of points. That's exactly what we're going to do right now. We're going to have basically the DTFT matrix, right? What is this? Row here represents? It represents really complex exponentials, right? That count n from minus n all the way to plus n at frequencies omega 1. Okay? When you multiply this with this, you would get the evaluation of the frequency response of this filter at frequency omega 1. Okay? This dot product with this one and then summed over, okay? Or a vector vector multiplication between this and this will result in the evaluation of the frequency response of this filter at frequency omega 1. If you just write down what is the DTFT of this filter at frequency omega 1, that will be exactly that equation. The second row will be the evaluation at frequency omega 2. The third row at omega 3. And so on and so forth till you reach omega sub p. That's the last frequency that we're going to evaluate at. So A times H tilde evaluates the frequency response of H at p discrete positions. Okay? If it was at m plus 1 discrete position, that would be actually the DFT matrix. Okay? But now it's at p position. It's really like zero padding and then computing a DFT. It's exactly the same. It comes down to be the same. Okay? The DFT, but it comes down to be the same. Okay, so now we constructed the matrix A, vector B, and the vector H, which we don't know. We want to find H. Okay? So what we want to find is this H bar, H tilde, that minimizes the norm of the difference between these two vectors, right? This is the frequency response, and this is the desired one. We want to find the least squares solution. This is a least square problem. Who doesn't know what the least square problem is? Okay. So this is a regular least square problem. Okay? And the solution for least squares is a pseudo-inverse, right? A transpose A, or it's not just transpose because this is a complex matrix, so it's complex. It's transpose conjugate. Okay, so A conjugate A, then you take the inverse of that, multiply by A conjugate times B. That is the least square solution that gives you the H tilde that minimizes that function. Very simple to implement. Once you constructed A, constructed B, you can get H tilde very quickly just by computing it either in Python, NumPy, MATLAB, whatever your favorite solver, to solve this inverse problem, okay, least square problem. Okay? Once it's discrete, then it's trivial. Okay? You construct A, you construct B, you compute this is a matrix. You multiply that matrix by B, and voila, you got the result. Simple. Okay? Now the thing is that the result will generally be non-symmetric and might be actually complex valued depending on how, what is the desired frequency response that you prescribe. But if we know that the desired frequency response that we want is real, okay, and symmetric, like often happens with low-pass filters, okay, the frequency response that we want is real and symmetric, then in that case, H tilde should also be real and symmetric. Is that right? Okay, it should be also real and symmetric. So in that case, we only need to solve for half a filter, right? Just to one side of the filter, and then we can just replicate, and that will guarantee our result. Okay? So here's what we're going to do. Any questions about this? How you construct this? Let me ask you actually a question. What will be B? What will be B? Is a vector of what? Let's say we want to design a low-pass filter. What will be B? What will be? It will be 1, 1, 1, 1, 1, 1, 1, corresponding to the passband omega sub I, right? For all the first omegas, it will be 1, and then in the passband, what will be in the don't care region? It will not be, because we don't care. We're not going to compute A in the don't care region, because we don't care about it. Okay? And what will be in the stop band? It will be zeros. Okay? So B would be a vector of 1, 1, 1, 1, 1, 1, and then 0, 0, 0, 0, 0, 0. Okay? That's it. And then this is basically just complex exponential with different frequencies. Frequency 0, frequency 1, so on and so forth. Till we finish the stop band, the pass band, then we go to the stop band, and that will be almost pi. Okay, omega sub p would be the one closest to pi. Okay? All right. Okay, so now what we'd like to do is design what's called a linear phase filter. It's a filter which is symmetric, and it will result, that will result in what's called a linear phase. In our case, it just means that the frequency response of this non-causal filter is just real. Okay? If we make it causal, it will just have a linear phase component, right? Because once we shift something in time, it will have a linear phase. Okay, it's modulating the frequency response. Okay, so this should be real and symmetric. We're also going to pick M to be even. Okay, so M plus 1 tap. So M is even, means that we have an odd size filter. Okay, if we pick M equal 12, it's 13 taps. Okay, there's a reason why we're going to pick this one. You'll see that this will be a type 1 linear filter when we talk about the types of filters. Okay, but when we get to this, we'll get to this in a few lectures. It doesn't matter so much now, but these are the constraints that we're going to impose right now. M is even, and this is real and symmetric. If that is true, then H tilde should be also real and symmetric around the midpoint of it. Okay, for example, if you think about a sink, right? Sink is real and symmetric around the midpoint. All these windows, right? They're real and symmetric about the midpoint. Okay, so then if we want to compute H e to the j omega, given the fact that H tilde is real and symmetric, okay, then I can just write down the frequency response. And the frequency response of H e to j omega is the sum from minus infinity to infinity of H of n multiplied by e to the minus j omega, right? Okay, so I'm actually just writing down the sum here. And I'm writing it in a different order. I'm starting at 0, and then 1, and then minus 1, and then 2, and then minus 2. Okay? So I'm still summing from minus infinity, or from minus n to n, because our filter is only from minus n to n. But I'm just reordering it. Right? A sum, I can reorder it, doesn't matter. Okay? So it's a sum from minus n to n, but I'm just reordering it. So the same sum is going to look like H tilde of 0 plus H of 1 e minus j omega, right? Because the n here is basically 1, plus H of minus 1 e to the j, e to the plus j omega, because it should have been minus 1, right? Because the n was supposed to be here. Okay? And then H tilde of 2 e minus j2 times omega, and then H minus 2, and this will be then plus, and so on and so forth. Okay? Now, the thing is, because H tilde is real and symmetric, H1 and H tilde minus 1 are the same. Right? Because it's symmetric. That's what symmetry means. And so if this is the same, then really what you have is E minus j omega plus E plus j omega. Right? And we can take this H outside. What is E to the minus j omega plus E to the plus j omega? It's a cosine. Okay? So that the whole thing here comes down to be H of 0, then plus 2 cosine omega H1, plus 2 cosine 2 omega H2, and so on and so forth. So by imposing this symmetry, now I get that the frequency response is real. Okay? Which kind of makes sense. If I have a real impulse response, real and symmetric impulse response, the frequency response should be real. Therefore, it should have this form rather than something with complex exponentials. Okay? All right. But now that I'm going to impose this form, and I'm going to impose a symmetry, I'm going to guarantee that I'm going to get a real symmetric impulse response in my solution. Okay? So now I have a don't care region. I'm going to set B to be 1, 1, 1, 1, 1 in that region. I'm going to set zeros to be, I'm going to set B to be 0 in this region. Okay? Then I'm given a certain M. I'm given certain W sub P, small p, by the way, and not W, omega sub P, small p, omega sub small s. This is the pass band. This is the stop band. Okay? And a don't care region. And now I'm going to build the A matrix out of, instead having complex exponential in it, it's just going to have these cosines. Okay? So 1 plus 2 cosine plus 2 cosine omega 1, and then 2 cosine in it 2 times omega 1, and so on and so forth, till I get to m over 2 omega 1. And then I change the omega sub 1 all the way down to omega p, which is the end of the passband. And then I start with omega sub s, which evaluates the frequency response over here, all the way to the last point. Yeah. You had a question?
Yeah, I was wondering how the factors out the down pair when you're like going from blue to red in the B portion.
I just don't compute the DTFT there.
So how do you know where WS starts then?
Well, that's part of the specs. Okay, that's part of the specs. Given M, W sub, omega sub P and omega sub S, I construct this. Okay, so I really don't need to include that in the optimization. Okay. Yep.
Why is the ground going from m over 2 times omega s to m over 2 times omega p?
This is capital P, so that's the last point.
Is that equal to pi?
Could be, or close to pi, depending how you break it, whether you break it evenly or oddly. Yeah, it could be pi, or it could be just pi minus 2 pi over p. Does this make sense? It's really easy. Right? It's really not hard to do. I mean, I can do that within 3 MATLAB or Python lines. Just do this optimal filter. Okay, so once I solve this, I get h tilde, but only in the positive part of it. Right? I only get the positive part of h tilde. I only get h of 0 all the way to m over 2. Okay, that is the result. Okay, I'm only going to get the positive part of it. And then I'm going to construct h tilde from this result. Basically, I'm just going to extend its symmetry. Okay, and get the entire filter, because now it's symmetric, such that h tilde is this for the positive, and it's flipped for the negative part, right? So now it's symmetric. And then to get the real filter, I need to shift it by m over 2. Okay, so now it needs to become positive. Now, this is cosmetic because once I have these taps, I mean, the way I implement filtering, it's fine, it works. But just mathematically, this should be, shifted. But you really, I mean, if that's the size of the filter and I filter with it, effectively that's what's going to be doing. Right? Yeah.
Does this mean why you can take just the positive or just one side of it and then mirror it, and that still captures the optimal solution?
Oh, well, because we described the impulse response as this, right? So now we don't have in the equation the negative ones, right? So we actually solve for less parameters. So the optimization gives me half the parameters. But I know the other ones. Right? I know the other ones. This optimization is smaller. Okay?
So we're not discarding information.
No, you're not discarding, but you implicitly impose it by using cosines instead of complex exponentials. Does this make sense? Really easy to do. Super easy and really, really efficient. Now the thing is, it doesn't have any preference for the passband or stopband. The penalty is the same on both the passband and stopband. So I need to do something. If I really care about the stopband differently than the passband, I need to do something. In order to do this, we use a weighted least squares. In the weighting, we put delta P in the passband and delta S in the stopband. Okay? And then, or we could weight the passband to be 1 and the stopband to be delta P over delta S in terms of what's the ratio between the penalty in those. If delta P and delta S are the same, then it's not going to matter. If I scale them, the optimization will be exactly the same. But if one of them is bigger than the other, it's really the ratio between them that we care. Okay? How much we care more about the stopband, how much we care about the passband. And so in that case, we're going to solve for h tilde plus this optimization, but we're going to use a W, which is a diagonal matrix representing those weights. And W should have on the diagonal 1 in the passband, and then delta P over delta S, which is the ratio of how much we want to impose between the passband and the stopband on the diagonal here. This is actually what would bias then the optimization to give more weight towards, if this weight is higher, then the penalty will be higher there. Okay? So if we're going to put more importance on the passband with respect to the stopband, then this will be positive. The opposite. Sorry. Yeah, no, this will be positive. And then if we want to impose more well, I guess you can think of delta P to be how much ripple you're willing to have in the passband. Delta S to be how much ripple you want to have in the stopband. So it's the opposite in that case. So if I want more ripple in the passband with respect to the stopband, then this should be positive, or sorry, bigger than 1. If it's less than 1, that means it's the opposite. Okay? All right. So this is a really useful way to design the best filter, given a least square constraint. And least square filters are actually pretty good. Okay? People use them all the time. But sometimes you'd like to design something else. For example, if you want to prescribe, I really don't want the passband or the stopband to deviate from a certain range. I really, really don't want it to deviate. All frequencies are really important to me. So I don't want to deviate there. Then the constraints are different. In that case, I want to minimize the maximum difference. So I'm going to look at all the maximum across all frequencies, and I want to minimize that. This is a different constraint. In this case, I have some ripple in the passband I'm going to allow, 1 plus delta P and 1 minus delta P. And there's some ripple in the stopband I'm going to allow, which is just delta S. Okay? So these are the specs now. No more deviation than plus minus delta P in the passband. No more deviation than delta S in the stopband. Now, how do I do this? Well, I'd like to minimize, for example, there's a few actually options there that you could actually do. Okay, in the passband ripple, I'd like my frequency response for a low pass filter to be between minus delta P and 1 plus delta P. Okay, that's a constraint. I also want to minimize it to be less than delta S in the stopband. Okay, so for those frequencies, omega sub S all the way to pi, it should be less than delta S. In the passband, it should not deviate from this. Now recall that H tilde is symmetric. So really, we only need to do that in one side. We only need to put constraint on one side of the spectrum. Okay? So now comes 127 material. For those that haven't seen it, basically this is a formal way to write this optimization. This is a formal way to write this optimization. This is a constraint that we have. We want our frequency response not to deviate between 1 plus some delta and 1 minus delta. We also want the frequency response in the stop band not to deviate between minus delta and plus delta. Okay? Now, what we really want to do then is minimize delta. If we minimize delta, it kind of squeezes this. It's kind of like a press. Okay? Optimization puts a press from one side and the other. What is the minimum that I can? Okay, that's what it does. It's a press. And we want to minimize delta. If delta is the minimum and it's positive, right, it cannot be negative. If negative, it's, it breaks. As long as delta is positive and we find the minimum delta, then this really satisfies the conditions. Turns out that this type of formulation is called a linear program, much like in the compressed sensing case that we solved, showed you that you could solve a linear program. I didn't tell you how to solve a linear program, but all I'm telling you is that you could solve a linear program. If you could solve a linear program, then you can pose this as a linear program and then solve it. And basically what you do is construct matrices. You construct A in the pass band, you construct A in the stop band, and you put these matrices in constraints. There's many tools to solve this. For example, CVX in MATLAB is a good one. CVX opt and CVX mod in Python. They have engines that are Sedumi. These are free engines, and some of them are commercial engines that solve the linear program. If you take 127, you'll understand how to do this. But here's just the MATLAB code that uses CVX, okay, in order to solve this. What you do is you have all these parameters about M. You construct these matrices, AP and AS, and then just write the optimization problem, and voila, you get the result. Okay? So this is kind of to encourage you. It's useful to take 127. Yes, it is possible to prescribe such constraints. If you need to, then you need to go to these tools and figure out how to do them. Okay? But it is possible, and it's actually not very hard to do in today's newer methods. And you can also prescribe really complex types of filters then in this particular way, whereas in the Parks-McClellan algorithm that is written in the book, it's really, really hard to prescribe these complex constraints. Okay, so with that, I think I'm going to finish today. We're going to move then to characterization of systems, and we're going to talk about phase response, frequency response, minimum phase, maximum phase, linear phase system, and so on and so forth. And that will be the end of the material. Okay, so we've got 4 weeks left. All right, so I'll see you on Wednesday. Please start on the labs. Okay, start on the labs. Thank you.